Okay, guys, last one, 6.4, telescopes across the spectrum. We're going to be talking about all the different telescopes we have that look at all the different electromagnetic spectrum, okay? And we kind of did that a little bit. Okay, so how do we look at this invisible light, okay? So different satellites, because, I mean, we see visible light. All the rest of the stuff to us would be invisible. Gamma rays, ultraviolet, microwaves, all those things would be invisible light to our eyes, right? So how are we going to be picking it up? So we use different ways of really reading these different types of light, okay? So this right here is a radio dish, yeah? And notice how it is built just like a telescope, okay? Now let's look at a reflecting telescope. Let's think of the idea here. You have a mirror that is curved on all sides like this, and then you have a little piece of mirror that shoots light into your eye, that where the light from the light comes, bounces off this dish, hits this little mirror thing, and then it bounces off to your eyes to see it. And we use a little like magnifying glass type thing to see it. The radio telescopes work the exact same way. Yeah, it's redirecting light or radio waves that hit this satellite dish and move it to right here. And this sensor is built to pick up radio waves, not visible light rays or anything. So they would all be built very similar to a regular telescope for visible light. They're just going to use different sensors that'll pick up that type of light. Okay. So here's the world's largest radio telescope. Notice this. Okay, we spoke about angular resolution is how big the telescope needs to be depending on how long the wavelengths are of the light. Well, radio waves are extremely long. So in order to have a very small angular resolution, or the ability to see between different things, you would need a really, really big telescope. So the largest telescopes you would find would be radio telescopes. And this is basically like the giant mirror you would have on the bottom of a telescope, and this is your little light sensor, but it's a radio sensor, a radio wave sensor, which is a light sensor, at the top of it, yeah? And so these are like what you're going to be seeing for radio waves. And you don't have to have it this big for radio waves. You can do something different here. Watch, I'll go forward to something called the VLA, which is the Very Large Array. And this is these are radio telescopes. There's a bunch of them. It's not very far from here. It's about maybe 2 hours. It's in Socorro, New Mexico. You would go north of here, okay? And you would run into the VLA, and they use a bunch of smaller radio telescopes, and they put the image together and make it act as though it was a very big radio telescope, okay? And it's called the VLA, the Very Large Array. Astronomers are very creative about their acronyms, yeah. Okay, so we also have infrared and ultraviolet telescopes, yeah, because those things don't get through the atmosphere. But now some, like we said before, some ultraviolet rays get through and some infrared get through, okay, but not very much. So in order to have like one of these telescopes, you don't have to go all the way into space. What you could do is you could just go above the atmosphere, most of the atmosphere, yeah? And if you go above most of the atmosphere, you could do that with like a plane or something. And you could, what they have here is, this is Sophia. It stands for, I can't remember exactly what it was, but it stands for infrared, the I believe. And what it is it picks up these UV and infrared light, and they don't have to actually send a satellite into space for it, because they can just use a plane that kind of travels above the upper atmosphere part of where UV rays get blocked out. Because remember I said UV rays get blocked out by the ozone layer. If you could fly above the ozone layer, you're good. You don't need to actually go into space. Okay, so let's see here. On X-ray telescopes, we have Chandra, okay? And Chandra does have to be in space, okay? Because no X-rays make it through our atmosphere, okay? And that's the X-rays and gamma rays, if I remember right, get blocked out by the magnetic field, okay? And to do these, you're going to they require special types of mirrors and different ways of focusing the light. Okay, so I mean, not everything's going to act exactly like a telescope would, like a regular visible light telescope, which you can see here. X-ray telescopes are a little different, okay? But they still focus the light into one spot, and then you have that light sensor right here that would pick it up. Okay, gamma rays, that's the Fermi telescope, and I'm not, it's, from my understanding, gamma rays are the hardest ones to build telescopes for. I'm not too familiar with exactly how it works on those. And we can also see other things that are just not light. Okay, so we also build these things. They're not really telescopes, but they're ways of measuring things. Like we have this thing called LIGO, and this is the way that they detect gravitational waves. Okay, and it's kind of interesting. What they do is they have a mirror way down here on this side, and they have a mirror way over here. And you would really need to see a video of it to kind of get an idea exactly how it works. But they shoot light all the way down this, and then it reflects off the mirror and comes all the way back, and they do the same thing on this one. Okay, and then if they come back at the same time, then that means that there was no gravitational waves. If they come back just like microseconds, and I'm talking like decimals of microseconds difference, then you can start saying that there was a gravitational wave, and that's how they pick up things like neutron stars colliding and black holes possibly colliding. And we have different ways of picking up different things. Neutrinos, we're going to talk about our neutrinos detectors next semester. And so we have lots of different ways to pick up lots of different types of light, okay? And gravitational waves would not be light. Remember, only the things on the electromagnetic spectrum would be light, okay? And we just spoke about the VLA. You can make a bunch of telescopes, smaller telescopes work together to act like a larger telescope. And we have actually done this before on not just radio waves, but we've also done this on visible light rays. And I know that you guys might have seen this. This was maybe a year or two ago where they took a picture of the black hole. And with a standard telescope, the telescope to view the black hole from here on Earth, you would need a telescope with the diameter of Earth. So you're not going to really ever build a telescope large enough to see a black hole. So what they did was they used different visible light telescopes all around the world, and took pictures of it at different times, and combined all those images together to create this image of a black hole, which I know it looks pretty bad. It looks pixelated. You can't see real defined. But the reason why is because we're basically, here's how it's been explained to me. It's the black hole takes up as much sky as if you looked at the moon and there was an apple on the moon. That's how much of the night sky a black hole takes up, the ones that we've been taking pictures of. So it's like trying to take a picture of an apple that's on the moon. Okay, and we can't do that. We're not even able to take pictures of the things that we put on the moon, like flags and things. They're too small to make out from Earth. The only way to get pictures of those things would be to have satellites that go up there and kind of orbit the moon and take pictures that way. But we can't even get pictures from Earth of things that are as big as a flag, let alone an apple. Okay, so that's why the picture's kind of pixelated and it's not very defined, is because it's a picture of a very small object. And that is it. I hope you enjoyed.